Okay, cool. So I think I just wanted to talk a little bit about the write-up for assignment 6, just so everybody has the answers. I didn't, I mean, I'm only about halfway through grading right now, but I'm not writing detailed responses. If you missed a question, I kind of just wanted to go over it here. That way, um, I don't have to write it up for every single one, just because I guess there is a lot to read on this one for the write-up and the memory leak and all that, and I figured it might be easier to do it that way. So if you notice when you see the comments when you get it back, I'll just put a number if you missed the write-up number, and then we'll go over the answers here. And then on top of that, maybe I'll wait a little bit longer to talk about it. Let's just get into the write-up first off. So from assignment 6, the first question we had was, what are the main advantages of operator overloading in terms of code organization, and why are they useful? So we don't really necessarily need operator overloading to do anything useful in a programming language, but at least like a practical sense, as far as like the code execution goes. But it's mostly just there to make it easier to read. Yeah. So if you said something along those lines, I guess I would have taken it. It's really just a nicety. It's there just to be more similar to how you would write things in real life, because typically if I wrote 4 plus 5, I would do 4 and then the plus symbol and then the 5 between it, and I wouldn't do something like add 4 5 isn't how I would typically write things in math. You don't usually use function names. You usually have those built-in arithmetic operators. So it's just there for readability. And then number 2, why must the extraction and insertion operators be friends of the class they operate on? This question I think was a little bit misleading, because this doesn't always have to be the case, I wouldn't think. They had to be friends here because we need to operate on the private members of the class that we're actually operating on. And the reason we have to do that here is because we didn't have any accessors. So you could totally get away with just using get something, and it would be fine. Plus, I guess, on top of that, we do require the number, or I guess big num was the class we had here, but we require the class type to be on the right hand side of the operator for both of those. It can't be on the left, right? You can't say, like num arrow arrow cout. So I guess we would also kind of need it to be a friend for that reason. So maybe it does always have to be marked as a friend. Maybe I was incorrect earlier. But yeah, I'll take the if you mentioned something about accessing private variables, that's fine. And the other reason, I guess, would be that if it was part of the class itself, then the operator on the left is generally implied to be the class type when you write an operator. As I'm sure you noticed on a few of them, I think equal had that, where it was like equal was void returning, and I think the left-hand side was implied to be the object calling it. So the order, I guess, matters there too. Number 3, explain why it is not possible to add new operators to the program, but only to overload some of the existing ones. And that question was a bit hard. I gave a bit of an answer for it beforehand so that maybe you would have an idea. And it has to do with the way that the compiler parses the program. And it does that based off of what's called a formal grammar. And the operators are actually built into that formal grammar. So the way that it parses it and figures out what exactly is that you wrote, what's a variable, what's an operator, is this a for statement, is this just a statement in general, is it a Boolean expression, that kind of stuff. It has that actually baked into the grammar itself that defines the syntax. So I can't actually not write that. And the example I gave, just to explain it more, because I gave everybody that x, a, y example. So let's just say I define an operator called a. Then if I wrote something like z equals x, a, y, because the compiler ignores white space, then this is all just going to get meshed into one big word. And at that point it becomes a little ambiguous because the compiler doesn't really know all the information about your program. So is this a variable? Is there a variable named XAY? Or is it that operator, or what exactly? Or is this maybe like a function name for some reason? So it's not really clear. I feel like there's something else I wanted to mention. So we can't even really do that with other symbols like operator. Like even if I was to do something that can't appear in a variable name like a quotation mark, then if I did something like that, then maybe it's the beginning of a string, because if I did this and then, it only really looks one character at a time. If it gets here and it's like, oh, maybe that's the end of the line because it's a semicolon, well, maybe there's another quotation mark after that. And now this is a string that contains a semicolon, and so there's some difficulty parsing that. And on top of that, then we kind of have an issue of how do we fit it into the precedence. So does it operate before plus? Does it operate before times? Is it after those? Where exactly does it fit? Is it a binary operator? Is it a ternary operator? How does that work? So there's a lot of complications that come with trying to add something that's not already built into the language, and that's why we end up just using the ones that are defined in the language by the syntax. Right, so the last one we had was describe why we need to overload the assignment operator and use a copy constructor. And so far, I'm pretty sure most people have gotten that question correct, which was just, I have a picture of it somewhere, but I guess I won't draw it for now. The reason there being that if you don't use that, then anything that involves a pointer with regards to those is going to be copied via the reference or the pointer, rather than the actual values itself. And so if you, which I noticed some people did, I guess, in the program, if you do just like left dot digits equals right dot digits in that program, then it's going to copy the pointer to that object, but not the actual characters that were inside of the array that digit's represented. And likewise, if I had maybe a pointer to a class type, if I copy it over, it's just going to copy the address, or in other words, the pointer to that object, but not the content of the object. So it's not going to copy over, like, if I had a person with an age and a name, it's not going to copy over the age and the name. It's just going to copy over the address of the area where those are located, which is a bit different and means that we'll be able to overwrite it later, which is not what we want. Right, any questions on those? I should hopefully have it graded within the next couple days. So the other thing I wanted to bring up, because I know I had a few students ask about it, is would you like to have a stream similar to assignment 1 and assignment 2 for 5 and 6, where I just go over like writing it up just from scratch? And if so, I was thinking this weekend, or either splitting it up over the next 2 weekends, so I guess it's kind of up to you. So if you have any input, just let me know. For sure. I'll probably do assignment 5 on Saturday then, and assignment 6 on Sunday, if that sounds okay. Or if you'd rather me split them up over the next 2 weekends, I can do that too. Yes. Alright, well, let's at least plan for Saturday then. Maybe around like 1 o'clock. I'll try and do Saturday and Sunday. Okay, fair enough. Oh, if you have input, either just comment it at some point, or I think there's still a thread on the announcements page that allows you to reply if you'd like to put it there too. Okay, so I might do Saturday and Sunday then. And I'll do at least Saturday, bare minimum. Yeah, I'll post it on YouTube. I'll stream it straight to YouTube, if anything. Alright. So that's kind of worked out. Let's talk about assignment 8, which is due next Saturday. So again, you kind of have a bit of time. I'm just going over it early for those of you who really want to get ahead, I guess. You can really do up to assignment 9. They're all posted up to assignment 9. We've gone over the material for that, so if you really just want to get it out of the way, I guess there's always that. But for the time being, here's assignment 8, which is just on exception handling, and conveniently, I think a lot of the code is already written for you. This one looked pretty good with that, actually. So you're going to get a file here, which is a CSV, and essentially it's going to contain a list of transactions. I suppose I should actually pull it up. So you're going to contain a CSV similar to the cars file that we had in the first assignment. So the first line is just going to be garbage. It's always just a description, and we don't really necessarily need that here because we have some sort of idea of what it is. And then you're going to receive a date, a time, and then a product, a price, how they paid, and then all this other stuff. I think I have this open in Visual Studio Code, so let me open that really quick. But what you're going to need to do is some exception handling. And there's a class already created for you called transaction, and there should be another one called date. So the date holds the stuff associated with the date, year, month, day, hour, minute. Excuse me. And then the transaction has a date that holds that, and then all the other stuff that was on that line in the CSV file. So you need to read all of that and then create a date. So you'll need to parse that as per usual. So, you know, I think the easy way would be to read a number up to this slash, read a number up to this slash, use S to I to convert, do the same thing here, and then read a time up to there, store that, and then read commas every single time. And then you'll see that these ones actually end with a comma at the very end, so you should be able to work with that. I don't know if this space here is intentional or not. Maybe it's just to make sure you actually have the parsing down. I'm going to keep it in, I'm not going to fix it. I assume it's intentional. Right, so you need to read all of those, store those into individual transaction objects. So each line is an object, and then there's a vector somewhere, I think he says, and I think I remember seeing it in the code. And then you'll store each of those into a vector. And then really the only other thing you'll have to do after that is just sort it using a generic template, and you're already doing that on assignment 7, so I think that one won't be too bad because you can kind of just copy and paste your code over, and you'll just need to change one line, which is the fact that the function itself for sorting needs to be a template function rather than the class. But you can kind of just copy and paste your code. It's not that big of a deal. I kind of expect everybody to write bubble sort, so I think it will look the same pretty much across the board for everybody, which I guess is to be expected, so not a big deal if you copy and paste from your last assignment. And then we'll need to handle a few exceptions when reading. So the prototype of this function is given here, so there's some sort of read file, and it's going to return the vector of transactions, so it's going to basically create it and then populate it and then return it, and it's going to get it out of this thing here. So where is it? Main file. Oh, these are the functions. So you have the read file, which actually does the reading, the parse, which just parses each individual line, And then there's a function called file size that I believe is already written for you that gets the size of the file in bytes. And we're just going to use that for error checking. And then the sort part that I mentioned. So this part will sort it. Actually, you don't even need the generic type, I guess, because it's just vector t. So it's captured there. You might actually need to put a template above this, I think. Actually, definitely do. Right, so there's a few exceptions that you'll need to handle. So there's a file not found exception. There's a big file exception. So this is where the file is too many bytes. So you'll see here, if it's more than 5,000 bytes, so you can use that get size function to actually get the size and then just check if it's greater than 5,000, in which case you'll need to throw a exception. And then there's a bad allocation exception and a length error exception. I think that's all of them. And an out of range. So this one, I suppose, would be if the vector you are going greater than the size. So you can check on something like this if the index you're using is greater than the length. After that, 3 different vectors are used to store the names. However, the size of vectors are legally set, which results in a... Well, I suppose it will make more sense if you look at it. So you need to throw those. I've put a list of exceptions on the assignment itself on Canvas, so you can see all the ones that C++ supports. Most of those are already exceptions that are handled by C++. For something like the bad file one or the big file one, that's not a built-in C++ exception. So you may need to either create a new exception or just use a random one and then catch it, which I suppose is okay, but usually it's better if you create your own exception. So if you remember, you can take an exception class and you can inherit it from it. So you could do something like exception : file, big file exception, and then you could throw that instead. Right, so here we have the date class, which I think is pretty straightforward. It just has all the parts of the date, and then he wrote an operator for you, and I think you'll need to do the destructor. And then there's a operator here, overload, to print it. And then we have main, where you have the function that you're going to have to write, so the parse, which just parses each line, and then the read file, which is mostly done for you, it seems. So that's pretty good. And then there's the sorting one, which again, you can just use the bubble sort from the last assignment. And so we're going to go here and basically throw exceptions as we have issues. So here, I believe you'll need to write the actual code in main. So you'll want to try and open wrong file. Oh, actually, I guess read file will handle this. So if you go into read file and you end up getting that you get any of those exceptions, then you're going to throw them and then catch them. So you'll need to put this whole thing in a try block and then put a catch underneath for each of the individual exceptions. So you'll need to catch bad alloc and maybe a big file exception and file not found and all that. So really, you'll just need to write a few functions here that do a little bit of code, and then you'll need a try catch block in this. So try around most of this and then catch right after it. I think that's about it. Any questions on that? I guess there's a write-up as well, but I took a look at the questions. I don't think they were too difficult. I think base class is design. Okay, that one is fine. Briefly talk about the advantages of doing exception handling. Yeah, I would say I think those are straightforward enough that I'm not going to talk about them. I'll let you try to figure that out. Right. So due next Saturday. Any questions right now? I know this is probably a ways away right now because we still got to do assignment 7. Don't see any questions, but I'll I'll assume you guys will have some when you start working on it. Okay. I think that covers everything that I wanted to talk about that wasn't new stuff. Okay. Let's just see how far we get with this today. We wrote a class a while ago that dealt with dynamically allocating memory. So it was that list type that we wrote maybe about a month ago, and then I changed it to be a generic type the other day so that it did with whatever type. So when I have a list and then let's just say some type T that I have, then what we said that did was it basically kept an array. So it had some array of type T. And if I had an array that was full, so it kept the size of it, right? So now it would be maybe something like 3. And it said if we try to add something, so if I had a function void add, where it tries to add something to the end, and it figures out that we don't have any space left. So in other words, the size is the same as the amount of allocated size that we had, so we probably had like a length and a size variable. Then if you figure out that you're about to allocate or run out of space, that you're going to need to allocate more. So what we did was we ended up doing something like new T, and then it was, you know, whatever length, so let's just say length plus 4 or some sort of constant, and then you allocated that and then set that equal to the array. So we would go in and we would allocate new space, right? So I would do something like this where I end up having the same array from last time, and then I end up having 4 more, so 1, 2. We'll just pencil it in there, that's fine. And then 4, and then we went and we copied over each individual element. So I said 0 goes here, 4 goes here, 6 goes here, and then we adjusted the size. So the idea with that was that we only ever allocated as much space as we needed for a list. So it wasn't like an array where maybe in 135 you allocated 100 things and then just, you know, maybe only use the first 20, and you were kind of limited by the fact that you could only store 100 max. So here we store about as much as we need, but it comes with the price of requiring the allocation at runtime and then also copying things over if we had a issue with running out of space. So I want to offer an alternative way to actually handle this that doesn't have to allocate space as often, and also comes with the advantage of the fact that the memory does not have to be contiguous. So consider that when we actually allocate an array, if this is my memory here, then when I do that line where it says r equals new int or t or whatever 4, then it figures out how many bytes t is and then allocates 4 groups of that many blocks. So let's just say t is 1 byte for the sake of making this look nice. So it would go and it would say, okay, this is t, and it would just put it right there. So it keeps track of, the compiler keeps track of some sort of pointer on exactly how big that memory is. Now, the problem with that might be that if we do keep it contiguous, then as I insert more and more things that are dynamically allocated and deallocate things, then I tend to run out of room. So maybe if this was my memory space, if it looked like this, and then I allocated, let's make this a little bit bigger. So if then I allocated something called R2, and it was a new, let's just say T of 2, and it goes here and it allocates this one. So let's maybe change the color on this. So this one was R, and this one was R2 for my allocation. Then if I was to go and delete R, which I don't think we've discussed the technical details too much, because look like that. But what it does is it does nothing. It just gets rid of the pointer and tells the compiler that it's allowed to use this area anymore. So it doesn't like wipe the memory. The word delete might be a little misleading. It really just goes and says it's usable again, and that's all it does. So it will basically get rid of that mark, that R1 that I had there, or R, and say, okay, now anybody can use this memory again. So when I do this delete, this is free to be used again. Now if I was to go and say R3 is equal to, so you'll see here we have 1, 2, 3, 4, 5, 6 blocks. So in theory I should have enough memory to create a new T6 and be able to store it. But when I go to do that, then the compiler is going to go and try to find the memory, and it's not going to find it. So we have 1, 2, 3, 4, 5, 6 blocks, but this one is only 5 here, right? So ideally what we would want to happen is we would just get all of these 6 blocks, but they're not contiguous, so it ends up not being able to do that. And moving around the other arrays is very time consuming and also just kind of annoying, so maybe we don't want to do that. So what I'd like to do is maybe not allocate things in a continuous manner, but do something where maybe if I was to allocate this array 3, then I can just put the elements here and then the last one there and kind of break it up. And we have a way to do that, and it's going to involve making each of the memory cells their own individual object. Now it does come with a disadvantage, or a few disadvantages, but we'll get to that. What I'm going to do is I'm going to create an object, we're just going to call it a node, and the node is going to contain 2 things. When you actually program it in general, you do it as a class type, and it's a very common, I don't know if I want to call it a data structure, but it's a very common object that you'll see in computer science is a node. And the node will contain a pointer or a reference to another node. So it's going to contain a node pointer, and it's going to contain some sort of data field. So I'm just going to call that T. So this is, again, we'll just say this is a template class. I'll probably just generically use T from now on. So class T, and that's the data. And for now, that's all it's going to contain. And that's a pretty typical structure for it anyways, is to have something like this. Now, this might not look too interesting right now because I'm just writing the code, but let's actually try to visualize this really quick. So the idea here is that we want to keep a list of things where each thing has an object and then a way to tell where in memory the next thing is. So if I was to use that other list that we had earlier, where it was 0, 4, 6, my new architecture is something like this, where I'm going to store 0 and then I'm going to keep the pointer to the next object in the list. 4, and then we'll just make it point down here, I guess, and then something like that where it's 6. And so at the end of the list we'll need, I'm going to use this notation now, it's just a line with 2 lines through it, which just means that it's null or it's not connected to anything. So what I'm going to need is I'm going to need some sort of pointer to the beginning of this list, and then now if I make these each their own individual class type, I'll be able to allocate them 1 block at a time, which means that I'll never encounter the problem of running out of memory when I still have it. I'll be able to allocate these things as kind of 1 block at a time. Right, so let's try to actually work out some of the operators that this thing would have, or some of the features that it will have. So let's just go over here really quick. When implementing this, it's a good idea to keep a few things. So you will need to keep that pointer to the beginning, similar to how the compiler gives you a pointer back to the array that you allocate when you allocate it. We're going to need to keep track of where exactly the head of this thing is. So we'll call that a head. It's a general thing. And then each node is just going to have that pointer and the thing. So what we want to do by default is similar to a vector. We want the object to start off as a length of 0. And the way that most people do that is we just initialize the pointer to null. So point it to nowhere. In other words, so if this is my head, then we'll just have it go nowhere to start with. Maybe I'll do it a little bit off here. And maybe I should put node int here, but let's assume this is using integers for now. So I'm going to need a few things. I'm going to need to be able to access elements. I'm going to need to be able to add elements to the list, and I'm going to need to be able to remove them somehow. So first, let's just go over insertion. Insert 4. So if I wanted to insert 4 into this list, the way it's going to go is something like this. We're going to create a new node. And when you initialize it, you're going to want to do two things. You're going to want to initialize the data field to whatever data you want to put there. So in this case, I'm going to put a 4. And then we want to initialize the pointer to null. And we'll always want to do that because we'll always assume that there's nothing attached to the end of an object just by itself. And then the next thing we're going to want to do is set the end of the list equal to the new object. So we'll see now that the head is there. And we'll write the code for it in a moment. This is just conceptually what we're doing. So let's say I go to do the next thing. And I go to insert, let's just say the number 6. In a similar fashion, we will create a new object, a new node. We will store the data in it, and then we'll initialize the pointer to null. And what we'll do here is we'll again set the tail pointer at the very end, to point to this new one. And there are multiple ways we could figure out the tail pointer. I'll give you 2 in a moment. But is that clear what this structure is, just to start with? Kind of? Fair enough. I mean, if you have questions as we're going through, let me know. Because we're going to hopefully make more sense on this as we start to write the code and look more at the other parts of it. I suppose I should actually tell you what this is called as well. So this is what you'll call a linked list. And it's a list because it dynamically allocates memory, and it's based off of the amount of things that you actually need, and it's linked because of these pointers here. Right, so maybe let's add the code for this. So is the insert function allocating a new node with the past int? Yes. Yep. Exactly. Yeah, let's actually write the code for that really quick just to make it clear. Let me go down here and write it. So what I'll write is, and this would be in the node class itself, but I'll write a function called void insert. And let's just assume all we have access to is, and I'll put an integer here, so we'll say integer n. So we'll say all we have access to is the head pointer. And that's it. That's all we have access to. So we'll assume that the class keeps some sort of static reference to the head pointer that we can access, just to make that clear. So what we need to do when we insert is we need to do two things. So we need to find where the tail pointer is, so where the very end is where it's equal to null. So notice that the end of the list is always null, and that's how we can actually tell that we're at the end of the list, which is helpful because now we don't need any sort of a length to figure out anything. We can always just know where the tail pointer is because it's going to be the null one. So we need to insert it at the tail pointer, and the tail pointer may be the head as well if we had an empty list. So remember that when we started this, we just had the head pointer, which was here in green, and it was just pointing to nothing. So we kind of have to address that specific case, because if that's the case, then there's no node for us to go to after this one. So let's just address that first. So what we'll do here is we'll say if the head pointer is null. Actually, I guess I should create an object first. So I'm always going to need to create that node regardless, right? So let's just say everything is public. Actually, I guess this is a member function anyway, so it's not a big deal. So let's just say we create a node called node. And so what I'll do is I will set the n.data. So the data that it holds, we'll set that equal to, oh, whoops. That's supposed to be called node, right? Let's make this clear. Let me make that an x, so we're not using the same letters. So I want to set the data of the node to whatever I'm storing inside of it, which is, in this case, we're going to say the integer that we're adding in. And then I'm going to set the pointer field, which I think I just called next, which points to the next node in the list, equal to null by default. So in general, this is how I would always start an insert function. Create the node we're going to insert and then figure out what we need to do with it. So what I'll say here is if the head is null, in other words, if the list is empty, this is empty, then what we want to do is we want to just make this new node the head now, right? So I would say the head is equal to node. I guess it would make more sense to do it this way. So node. And you'll see some people maybe just make this a pointer instead, which maybe makes more sense in hindsight, but this should work too. So this is a pointer, so we need the address to this thing. So what that would say is if we went and just added the 4 at first, if this list was completely empty, so if the head pointer, which is this part in green, was null, then what we want to do is create the new node, set the data field, set the pointer to null, and then we change the head pointer to now point to the first thing that we're inserting into the list. So that's kind of like an initialization step. We need to set the head pointer if it's not set already. So the other case would be where we need to insert it at the end of the list. So if something's already inserted, like here, then what we need to do is we need to figure out where this is exactly. So if I was to go and reinsert 6 here like we were doing earlier, then again, my first step is to create the node, initialize it, so I set the data to 6, the pointer to null so that it points nowhere, and then I need to make this one point to that one, right? So I need to make this tail. I need to figure out where it is exactly, and then I need to make it point there. So there are two common ways to do this. Either you keep a separate pointer in your class that points to the tail, which is, I think, a good idea. I would say that's a better idea than the way I'm going to do it in a second. or we traverse the list and figure out where the tail is. So what I do recommend is keeping a reference, like in your class here, like how I said head. No, this wasn't the right slide. There it is. So in my class I had next, oh, I didn't even write it down. We'll keep a static node pointer called head that points to the head. What I recommend doing is keeping a static node pointer that points to the tail, not the null part, but rather the object where that tail is located. And you'll hopefully see why I do that in a moment, but I'm not going to actually do that for our implementation, just so we get kind of an idea about linked lists first. So if I was to keep the tail pointer, it would actually be pointing, so on the last step it would actually be pointing here, and then after I add 6 it would be pointing here. That way we can immediately jump to the end of the list and we don't have to do any extra things. Right, so the process seems to be that we need to find the end somehow. So let's say I was trying to find the next thing, so if I was to go and insert 7, I'm going to need to figure this out somehow. Does anybody have any suggestions on how we might be able to figure out where this is if we don't just keep track of it? Is there any way I can get that, given that I actually do have the head? So the head is the only thing I have. So I want to start here and end up here. Maybe what I can do is I can follow this arrow and then follow the arrow after that. And then if I try to follow the next arrow and it doesn't go anywhere, then I know I've hit the end of the list. So the general idea when we go to traverse a linked list, so if I just had a really long linked list like this, with some sort of starting head pointer, is I'll just follow the arrows until I can't follow them anymore. So if I was to do a traversal order for this hypothetical list here, I would go to this one, and then to that one, and then to that one, and then to that one. So I'm just going to follow these arrows, which are the pointers, and once we figure out that we've hit the end, in other words we can't go anywhere anymore, then we know we're at the end of the list and we know that this is the tail pointer. So the way I'll do that is, let's just say I'm going to create a node called current. I'm sure there are multiple ways you could program this. This is just the way I normally try to do it. So we'll say node current, and we'll just initialize it to the head. So we'll say we'll start at the head of the list. Actually, let's make this a pointer. Node pointer current is equal to the head pointer. And so what we'll say here is while the current node that we're on, its next pointer, which points to the next object in the list, while that's not null. In other words, while we're not at the end, then what we'll do is we'll say that current, we'll overwrite it with the next one in the list, which would be its own next pointer. And then by the time this while loop is done, it will break once that current.next is equal to null, which is when we hit the end of the list, right? So it would be this node right here, that node right there, in those two examples. These are the nodes when that part is null. So the while loop will break, And then current will be pointing to the tail, the very last thing at the end of the list, which means that all we have to do is set current dot next equal to, oh, I guess current is a pointer, huh? So this is an arrow. Is going to be equal to the node that we wanted to add. Which up here was the node we created, was called node, right? So a lot of code doesn't all fit on screen. But the idea is we follow this all the way to the end. Once we get to the end, we add something new. So if I was to go and add this 7 now that we kind of have an idea of the process, we know we create the node. We know the list isn't empty. Oh, sorry, we create the node and set this equal to null. We know the list isn't empty, so we're not setting it equal to the head. And then we know that we want to add it at the end then, so we would follow along this line until we reach this point. And then we say, this one has a null pointer pointing to the next one. That means that it's at the end, so this is my tail. And what I'll need to do is set the pointer for that one, which was the next pointer, to point to the node that I just created, which was this one. And then now the list is done. And we have a new thing where the end is null. So that's why I always initialize the node pointer to null whenever you create a new one, because if we're inserting it at the end, then we know that that will automatically mark it as the end if the pointer is null at the very, very end there. So any questions on that so far? On the insert part? I think I'll hold off on programming it for a moment. Okay, again, if you have any questions, just let me know. So that covers one thing, which is the insertion. Let's do the get. And there's a couple ways we could do this. We could do this by looking for a specific object, or we could do an index. So maybe we'll do get at, and then we'll have an int index. So this way is going to be pretty much the same. You'll notice that we'll traverse it in the exact same manner every single time. The big problem, I would say, with linked lists, which is why we don't use them as a data structure for storage like an array very often, is that the lookup for things is very, very slow if we keep it in this manner that we're keeping it, which is kind of like basic of a linked list. So again, I'll say that there's a head pointer here, and we want to access something. So if I was to think of this like an array, this would be index 0, index 1, and index 2, right? The problem here is that unlike an array, I can't just jump straight to where the data is located. So if I had an array that was the same length as this one, it would look something like this. And part of the great thing about the fact that we use pointers to allocate an array and they're all contiguous is that I know exactly where everything is because they're all right next to each other. So if I said r sub 2, then it will really just fill in where that address is by jumping 2 blocks ahead of where the head pointer is. So array accessing is very fast, and it's pretty much just one step. You just go right to where you're told and you get the data, and it's done, and it's fast, and it's good. But on this one, we don't have that advantage because all we're keeping track of is the head pointer and possibly the tail pointer. So if I want to get something from the middle of the list, I have to every single time follow this, follow that arrow until I hit wherever I'm going. So if I wanted to get to R sub 2 in a traditional array, then that would take one computational step, which is just go there. But on this one, it's going to take 0, 1, 2. It's going to take 3 steps to actually get to R sub 2. And that's kind of the disadvantage of doing this linked list. So we get that memory advantage, and we'll end up using this and modifying it to actually do some pretty good things that are actually way faster than an array would be. But this baseline setup is kind of a bit slower. But let's at least try and figure out how we would get something here anyways. I guess the convenient thing about this is we know that we'll really just need to follow the pointer the amount of times that the number is. So you'll notice here, assuming I started the head pointer, then this is the head pointer, which means that if I need to follow it 0 times, then I'm already where I'm at. So if I follow the pointer 0 times, I'll end up at the 0th location. If I follow the pointer 1 time, which would be going down that one, then I'll reach the first element. If I follow the pointer 2 times, then I'll end up at the second element. So I won't account for error handling here, but let's at least just do the basic setup for this. So maybe what I want to do is, again, keep some sort of pointer to the current node, and we'll say that's the head by default because we always want to start at the head, and that's really all we have access to. And then we'll say while, actually, I guess I don't need a while loop. So we'll say we just want to go and we want to follow that arrow the same amount of times that the index is, and it will get us to wherever we need to go. So if I said for int I equals 0, I less than index, I plus plus, then that will count how many times we need to follow the actual node itself, and then we'll just say, so I guess I need another, no, I guess I don't. We'll just follow the node like we did on the last example. So we'll say current equals current next. So we'll get the next pointer. Kind of cutting into that. And then if we do that, we'll follow it index many times, right? And so by the end of this, we will know that the current one we have is exactly where we want to be. Right. So that should work. So this, I guess I didn't put here, but this would return a node. So maybe I'll just do that. That should be okay. Any questions on that one? So we just want to follow the pointer how many ever times the number is that we get, and that will give us the same location. And so you could write an operator overload if you really wanted to make this look like a array as well, if you wanted to take that index in for the bracket operator, which we didn't do in assignment 6, but is something that you definitely can do. Okay, so then really quick, let's just talk about the last major operator. Actually, maybe I should bring it up first. If I wanted to do a search or a lookup, then I wanted to like maybe match each of these, then note that you could just go through the array in the same, or sorry, go through the linked list in the same way where you say current equals current next, and then you could check if the current dot data is equal to whatever you're looking for, if we wanted to do some sort of lookup. Right. So I don't think I'll program that, but just something to keep in mind, or write it on the way out. So we've done insertion. We've done lookup or getting something at a specific index. The last thing we need to work on is deletion. What if I want to remove something from the list? Then we might actually have a bit of a issue. So there's one kind of easy case, which is we delete the thing at the end. So if I said head.delete at position 2. So we know this one's 0, this one's 1, this one's 2. Then that one's kind of easy because all we have to do is really cut this off and then set that equal to null, right? But what if I want to remove the 6? Now I'm going to have a bit of trouble because if I remove this 6 here, I need to change this so that it points to there, right? And with the way we've been doing it, we've been traversing one at a time, and we only keep track of the node that we're on. So if I was to go and delete 6, then my traversal order is going to look something like this. I'm going to point here, and then I'm going to go to the next one, so I'm going to point here, and then I say, okay, that's good, I'll delete that one. So let me change this to 1. So if I was to delete the thing in the first position here, then I'll have this pointer to it. I'll go and I'll delete it. So I'll just deallocate it or whatever. And then I just have a pointer to this thing. And now if I just delete it straight off the bat and don't do anything, I've lost this pointer, which was pointing to that thing. So now I don't even know where the whole rest of the list was. And I also don't have access to the one that came before it anymore. So I have no way to go back either. And so I just created a memory leak, and I lost all my data. So we're going to need to be smart about this. We're going to need to do some things here where we account for different scenarios. So this is probably the hardest part out of this one. So we'll say void delete. And then again, we'll just do it in an index. So what I think we should do here is we should keep track of not only the current node that we're on, but the node that came before it. That way if we delete something like 6, we still have a way to go back and look at this object here and figure out where its pointer is. So for this one, I'm going to create 2 node pointers. We'll call one last. And I'll set that equal to the head by default. So we'll say the head is the last one, and then we'll make the next object in the list automatically that one. So then we'll say node pointer current equals head next. We could do it that way, or we could potentially also do it with a null. I'm just thinking about which way might be easier, because I mean, we could do it either way. So if I was to make this current, then I could make that null. Yeah, actually maybe that's easier. Let's set the null equal to, or sorry, the last one equal to null by default, and then this one to head. We could do it the other way, we just need to consider one special case. And I guess I don't really want to do that. Okay. So what we're looking for is the actual index where the thing is located, which, like the last code, is just going to be exactly the same. So we'll say something like for int I equals 0, I less than index I plus plus. And then now we'll need to set both of these pointers every time we do something. And I know I'm just writing this generically with the int I, but consider that you would need to do some error checking, because if the index is out of bounds, you'll need to check to make sure that you don't hit null sometime before that. So maybe something that you want to consider here is the error checking, which I'm not going to write, but I just want to make sure everybody's aware that that would be a thing you need to consider. So what we'll need to do is we'll need to set the last is now going to be the new one that we're on. So if we move forward, then the current one will become the last one, and then the current is going to become the next one in the list. So current equals current.next. We could also say last equals last next. That would work too, but I think this is the way that I typically write it. Right, so what this says is if I had current pointing to there and last pointing to nowhere, then what I'll do is I'll set last equal to current, so it will point to the same location that current is currently at, and then current will go to the next one after that. And the order there matters. If I did it out of order, I would actually have an error, because I would be setting last equal to the next current, which is not what we want. So hopefully that's fairly clear what's going on there. So we'll just need one to point to the last one that we're at, and the one to point to the current one that we're at. And so again, by the time this breaks, because we have this for loop where it just goes index many times and then stops, then we know when it stops, it's going to be at the pointer that we want. So if this was to execute on this delete 1 scenario, then we know we're going to end up at 6. So there's 6 pointer here, which is where current currently is. Now what we want to do is we want to not just jump the gun and delete this immediately. What we need to do is we need to update the list so that this now points to that, right? And yeah, that's about it. We just need to delete that and make sure that the last one points to this. Right. So actually, let's think about the other case here. So if I was to delete 7, just consider that then the last pointer would be here, the current pointer would be here, and if I try to set this equal to the next thing in the list, then it doesn't work anymore because there's nothing after 7. So what I want to do really quick before we write the full code is just address if the next pointer has a null, then we're not going to do anything with it. So what we'll say first is if current next is null. So in other words, if the one that we're deleting is the end of the list, then we're going to have to do something special, and we'll come back to that in a moment. And then we'll have an else here. So if we delete normally, then what we said we wanted to do, let me just draw it over here so it's not something I have to keep scrolling up to. So what we said we wanted to do was, if this is the current one that we're pointing to and this is the last one, then what we want to do is we want to modify the last one to point to the next one. So we're going to sever that tie and then move it to point there. And then after that's done, we can delete the current node. So this is the reason why we kept the last pointer, is now we can say that the last, we're going to set its pointer equal to this one, which is the current pointer, which is that blue one. We're going to set that equal to the current's pointer. So this will redirect this red arrow to now point to the next object. And now the list is correctly assembled. We've separated cur off. We've kind of cut the link there, right? If we kind of consider what it looked like originally, this was pointing there and that's pointing there. We've cut this off, so it's now separated from the list, which means that it's now safe to delete. So what I'll just do is I will say delete current. And you want to make sure in your destructor that you're not actually deleting the pointer, the next pointer, when you're doing this, because otherwise notice that this is still pointing to the list, so if you do that you're going to end up killing the list. So in this case we actually have a destructor where we're not going to delete any sort of pointer. So this is kind of an exception to what we've been doing so far in class. You don't want to delete the next pointer when you do the destructor, otherwise you're going to get just a list that doesn't work anywhere. Right, so now that works. If it's in the middle of the list, it will just redirect the arrow around the thing that we're deleting and then delete the thing. So the other case we had was if this was here and we wanted to instead delete something that's at the end of the list. So if I have this one here where this is the current and this is the last and this is null, then we need to do something different here. So what I need to do is, it's already at the end, so I can kind of just delete it like normal. The only thing I really need to do is now, if I was to remove the last part of the list, then I need to set this equal to null. Which, actually, you know what? I don't even think I need the else statement, because if you notice here, this actually does the same thing. So this says the last next, which is that pointer, is equal to the current next. So, you know what? This should be fine. I don't think I need anything extra. I don't need to set the previous one. Yeah, that should be okay. Let me move this up then, so that it's... So it actually lets me. The library? No? I don't know how that works. Oh, let's just rewrite it really quick. So I should be able to just get away with that code. Now you would actually, I guess, have to do something extra if you were using that extra tail pointer to keep track of it. You would need to update the tail pointer if you are deleting the tail pointer. I think that's why I thought we needed to do something different. So if you do that sort of implementation where you keep track of where the tail is, just consider if you're deleting the tail, you need to set the tail equal to the last part. Okay, but that should take care of that. So now we've gotten all the major operators out of the way. So we did insert, we did lookup, and we did delete. And as you take more CS classes, you'll notice that a lot of the data structures we use, those are the three things that we kind of care about when we work with them. Right, I don't know if we want to program this just given the fact that we have 5 minutes. See if there's anything else we want to talk about. Or are there any questions? Should I start? Maybe scroll out a little bit. try to post these on Canvas too. Right, so any last things I want to mention then? We did insert, we did delete. No, I think we'll just talk about it more next time. So if you have any questions, feel free to ask. I'll stick around for another 5 minutes. If not, I'll see you on Monday, and I'm going to do the stream at least on Saturday, probably on Sunday for assignment 5 and 6. And yeah, I think that's about it. So if you don't have any questions... Oh, you have a question about the current assignment? Yeah, feel free to ask. How would we access the arrays within each of the bins so that we can print them out? Let's take a look at the code. I think you have direct access to them, right? So I think it's in the bucket class. Right, so you have a pointer to the array and it's protected, which means that you'll have access to it in the bucket, static bucket, and dynamic bucket. So you can actually just traverse it exactly like you would a normal array. So really you can just do the whole for int I. Do we keep track of the length? I guess that's kind of the important part here. I equals 0, I less than length. Because if we don't, then that's a bit of an issue. We have a get size function, which returns the size of the thing. So this get size, I assume, will differ depending on... Oh, no, we have a size variable. Okay, fair enough. I guess we don't really need to write anything special for that. So, yep, we'll just say I less than size, I plus plus. And then we'll just say cout. I think it was just called R, right? Sub I. And then maybe just put a space or something. So really you can just do it in the same way. The fact that it's template doesn't change how we access the array because it is still just an array, and the compiler generates the code based off whatever type you've written so far. So even though, I guess the other thing might be the fact that I'm writing this just normally with the cout, it will figure out what type it is. So the fact that it's a generic type doesn't change much because the compiler actually, it doesn't do anything at runtime as far as this type goes. When you do this here, this class type, and then I write something like bucket angle brackets int in something like main, what it will do is the compiler says, okay, the programmer is using a bucket that is going to store ints, so what I'm going to do is I'm going to just take this code that describes a template class, I'm going to copy and paste it, I'm going to return the, or replace the word type with integer, and then I'm done. So it actually goes and physically makes the code associated with that type. So really, when you do something where you use it like normal, it still works the way it would if I was to write a bucket class where it specifically stored ints, because the compiler does just straight up copy and paste and replace the type name. If that answers your question, hopefully. Oh, maybe that's just for like printing a header. So you just would cout the bin name, and then you would cout everything else like normal. Yeah, I think that's just to tell you what bin it is. But yeah, the printing itself of the actual contents is pretty normal. Alright, any other questions? Alright, I guess on that note, I will see you all either this weekend